So in this video, I'm going to go over the solution for the recitation problem number 1. And recitation problem number 1, I'm going to change the number slightly around, but the basic idea is that we have a spring connecting a mass M attached to a wall lying on a frictionless surface. So we have a spring attached to a mass M, and we're basically going to pull this mass. So this is at equilibrium, it's at rest. Now I'm going to pull it a distance, let's call it a distance of x. So here's the mass at a distance x, and then I let it go. And if I let it go, this mass, right, should be oscillating back and forth, right, performing simple harmonic motion. So we're expecting that. Here's a little diagram of the problem. We're also told that the mass of the object, and I'm going to change the numbers around slightly, right, so that they're not exactly the same as in the recitation. So I'm going to say this is actually 1.2. Let's put it down as 0 kilograms. And we're also told the spring constant of the spring. So here's our spring constant. The spring constant happens to have a value of something else, right? So let's make it 6.5 newtons per meter. Okay, and we're also told the mass and of course x. We're told that x happens to have a value of let's make it as 20.3 centimeters. Okay, so here's where we're going to start the problem off. Now the first step, right, is we draw a little diagram for the problem, which I did right here. It's not very good, but it's not meant to be. It's just something that you can actually visualize and make sure you understand the problem well. Now I've written down all of what's given to me. Here's the mass of the mass. Here is the spring constant, K, 6.5 newtons per meter, and x is equal to 20.3 centimeters. So this is what's given. First step you should do, right, in all these calculations is convert these calculations into standard units. We're always going to be using SI units, so do you notice that just kilograms is okay, newtons per meter is okay, but centimeters is not. So we should write this in terms of, remember, 20.3 centi. Centi is an abbreviation for 10 to the minus 2. So we're going to be just writing 20.3 times 10 to the minus 2 meters. Now we're in meters. And if you want to make this into a power 3 properly, you could actually divide by 10 here and then multiply by 10 over here. So dividing by 10 over here is 2.03 times. So divide by 10 and multiply by 10. So times 10 to the minus 1 meters. So now are in standard units. So the first part of the problem asks, find the force. Okay, so we're going to find the force, right, acting on this mass that's pulling it back this way. So our problem is F. So part A, right, we know that the force, right, so a couple of things. Anyway, force is equal to minus kx from using Hooke's law. So we already know what the force constant is, the spring constant. We know what x is, so we know we can calculate the force. So the next line I'm going to actually do the calculation as write the equation, never put numbers directly in, write the equation, get in the habit. So we don't know if the force, we're going to find it now. So K happens to have a value of 6.5. Because we switched into standard units, right, we don't have to worry about the units in actually number calculations. We know the answer is going to be in standard units. So it's 6.5. There's a minus in here, right? And x is given by 2.03 times 10 to the minus 1. Now a couple of things. Whatever the answer is, right, do you notice all these numbers have, these are 2 significant digits and 3 significant digits, so the answer is going to be in 2 significant digits. So actually I do have a calculator here, so let me just plug these things in. So 6.5 multiplied by 2.03 to to the power of 1 minus equals 1.3. So I get an answer of 1.3195. But remember, this has only got two significant digits, right? So we expect the answer to be two significant digits. So we should write this as 1.3. The standard units for forces are newtons, so the final answer is newtons. Now, if you actually put the units in, you can say newtons per meter, there's a meter here, and the meters cancel, right? But that's very time consuming. So just get in the habit of doing standard units first, and then put the numbers in, and evaluate the answer, make sure you get the right numbers and digits. So part A says, and of course I made a mistake, there's a minus in here, so minus. That minus means that if x is increasing this way, the force that's pulling the spring pulling back on the mass is negative in the opposite direction. So this is positive as x is increasing this way, and the force is acting in the negative direction. So that's part A. So the next part, right, asks, what is the acceleration if I let go? That's what I'm assuming the problem states, okay? So if I let go of the mass, it's going to start accelerating. So part B. So we know that force is equal to minus kx. This is Hooke's law again. But we also know force, right, is equal to mass times acceleration. So I can write this as mass times acceleration equals minus kx. And I'll put a little check mark on all the variables that we know. So we know the mass, that's given. We know the k, that's given. Here's the x. So a is the unknown, so I can solve for it. A is equal to minus kx over m. And now I'm going to start substituting all the numbers in. So again, we're going to write k. In this case, it's 6.5. You don't have to waste time writing the units in, because we already know what the units are. So it's all standard units. So 6.5 multiplied by x, which is 2.03 times 10 to the minus 1, standard units. Okay, don't use these numbers. We're using the standard unit numbers. And the mass happens to be 1.20 kilograms. So again, I'm going to bring out my calculator and calculate. Notice I'm not reducing all these numbers into their, so the smallest number significant digit is 2, so you might think I should only use 2 significant digits, but the general procedure is we calculate the numbers without using any significant digits. Only in the last step do we actually say we're going to reduce the answer to 2 significant digits. So here is, well, there's a minus here, right? So let's not forget the minus. So 6.5 multiplied by 2.03 exponent to the 1 minus divided by 1.20 equals, okay, so I get an answer of 1.099, and I'm overkilling it, but I'll just put 99, okay? And but remember, we only have an answer to 2 significant digits, so we need it up to here. So the 9 pulls it up to 1.1, so this is actually 1.1. Standard units for acceleration is meters per second squared. And that's your answer for recitation problem number 1.